Okay, I'll go ahead and start doing it. Give me a thumbs up. Okay, got a thumbs up. Okay, what I want to do is talk about, come up with a few topics that I'd like to discuss over the next few months. And one of them, the first one, is the cascade noise figure. And that's an equation by Friis. And I wanted to discuss it a little bit, and then I'll tell you how to do it without going through the equation. But quite often the comments arise about how we do the preamps down at the site. And a preamp here, I'm referring to something that is extra from a regular radio. It's something that you mount up at the feed antenna, and so there's very little loss in front of the front stage. And so I'm going to go over the equation here a little bit, talk about that for a few minutes, and then we'll go on through and I'll give you some examples and where to get the equation, where to get a calculator for it. So if you can see the cursor a little bit here, the noise figure equation up here deals only with the linear equivalence to the decibel scale. So in other words, nothing up here is in decibels. It's all converted over to a linear number. So the FN stands for the total noise factor. Now, once you get that number, then you go back down here and you take this equation right here, and then you can get the noise figure in dB of the total system. This includes the preamp stages, the filters, the losses of the cable coming down, and the SDR. Now, I don't know which SDR we're talking about here, so I just guessed and took a typical number for the little SPI SDR, which I had a number for. So anyway, the first stage, this one is the total noise factor that you're looking for. The next one is the noise factor of the first preamplifier stage. This is the second stage right here, and that amounts to a noise figure of the second stage -1 divided by the gain of the first stage. Now, and also you sometimes have to account for the loss of the filter in between the first and second stage. I'll show you that here in a second. And then we go on to the third stage, which would be the typical SDR in our case. You know, whichever one we decide to use at the time. So F here with the parentheses mean F1, F2, F3, and G is a stage power gain. These are both, F's are all noise factor, and the stage power gain is also in the linear units. In other words, if you had a 20 dB power gain, that would be a gain of 100. So you'd put 100 in here rather than the dB. Did somebody have a question or comment? Okay. Now here are the equations down here. So noise factor is equal to the noise figure in dB divided by 10 and 10 raised to that number. So for instance, if you had a 3 dB noise figure and divide that by 10, that's 0.3. And if you raise 10 to 0.3, you come out with a noise factor of 2. So that's in converting decibels in your head to noise factor, or to the numerical equivalent factor. You simply only have to remember two numbers. 3 dB is equal to a factor of 2, and 10 dB is equal to a factor of 10. And then you can figure out everything from there in your head, but we'll go over that some other time. The gain, of course, is computed the same way. And the noise figure, getting back from noise factor back to noise figure, is done with this last equation down here. So this equation does not deal with any dBs. So you got to convert everything down here and then plug it in, and then take this number that you get when you're all done and convert it back to the real noise figure. So that's the equation right there. Now let's go on to the second stage here, the second slide. These are 4 places where you can go on the internet and get that, get an equation solver right on the screen. It'll help you out, and we'll make that available on the website, I guess, or something like that. But anyway, I use this last one down here as being the one I use to calculate all these numbers. Understand that these sites also have a lot of other calculators related to our design. So you have a good time just going over and looking at these sites. They're very, very helpful. Going down to the third slide then. So our current preamp example, we have a two-stage 365 megahertz preamp that resides right up at the right behind the 4-turn helix that I use right now, and that's on this frequency. The stage 1 is a mini circuits amplifier with a 0.4 dB noise figure and 22 dB of gain. And I go through a bandpass filter, which actually is comprised of 2 filters, a low pass and a high pass, so that we come up with a fairly good bandwidth of about 100 megahertz up there. And that I just put in a number 2 dB loss because there is a little bit of ripple to it. So anyway, we'll use that number right there. Now the second stage also resides up at the feed, and that is another mini circuits amplifier following the filter, and that has a 1 dB noise figure with a 20 dB gain. Then we have to add in or take account of the line loss, which at this frequency down here is about 4 dB. We have about 200 feet of Heliax, but it's a Heliax RG213 combination as we get around the axis movement. And then we have a receiver. This is a typical kind of receiver SDR that has about a 5 dB noise figure. We don't have to associate a gain with that, but just the noise figure. And the results, overall noise figure, with this up in the front end, a 0.4 dB noise figure up at the front end attached to the antenna, the total system noise figure with all these losses and gains and everything still comes out to be 0.41 dB, which is very good. It's about 29 degrees Kelvin temperature. And so we did see some pulsars, and we were able to detect them here. But we have a lot of more interference as we get time with this thing and watch the signals on the band. Turns out it's a lot noisier than I had ever expected. So we may have to move again to find another frequency that's quieter. But nonetheless, the equipment did work okay.
Ray, can I ask a question?
Sure.
Why do we need the second amplifier?
Very good. In this particular case, we might not need it, but the more gain that you have up here masks this loss coming down the coax. Now, when we're up at 1420, we have about 10 dB worth of loss. So, for instance, this last noise figure contribution would be only about 10 dB gain, that we'd actually lose 10 of that coming down the coax. On this particular frequency, I'm estimating we have about 4 dB loss total. So it just turned out to be that I wanted this noise figure or this gain combination to be fixed, and we could change filters simply. These are very wideband amplifiers. So by using a bandpass filter, I restrict it to keep some other interfering signals from causing intermod problems. And so I want to make up the gain of this too, because that subtracts from this gain up here. And that's a little bit less gain than I'd like to. I'd really like to see about 40 dB gain, typically out of my preamps up there. And quite a few of the commercial ones we have at least 30 dB gain. But on mine, I like to build in about 40 dB. And you're going to see the result of what I'm talking about here in the next couple of slides.
Say, Ray,
Yeah,
this is Bill. Let me ask a couple dumb questions. Does the bandpass filter have any noise figure?
no, it's a loss.
So it's just a loss.
It's
So,
not, yeah, that does not have any gain. Yeah.
okay.
It's just, ideally speaking, they're lossless components. They're capacitors and inductors,
Okay.
and they're lossless, but that's in real fact, it's not the case, but it's very small if you build them right. You can buy the bandpass filters as well, but
Because when we
so
when we
we
talk
just have a little
about
bit of loss.
okay, when we talk about a noise reference, we're always talking about a resistor. And so there's a non-gain element that has a noise figure, right?
Sure, right. But in this case, um, we don't really have any resistor in front of the front preamplifier.
Yeah. So
And so therefore it's below, it normally would be, if you think of the noise temperature of all the parts up there, if it were a resistor, it would have a Kelvin temperature of 290, but without having any resistor components in front of it and any lossy components, the noise figure of modern day transistors and ICs can get down well below 1 dB. And in fact, we can get down to much lower than what we actually have right now, but these are fairly common off-the-shelf parts.
okay.
So then we go on. That's our current preamplifier up in the dish, but I wanted to add a 6-meter example that Paul is using down there. So Paul has an advanced or applied receiver research, advanced receiver research, I think, preamp, and it's about a half a dB noise figure and 24 dB a gain. It's a model number P50VDG. And so what I'm going to do is I'm going to run this equation with no attenuator following the preamplifier, a 10 dB, 15, 20, and 24 dB attenuator after the preamp. Most often these guys want to get rid of some of the gain because they don't need the extra gain. So the SDR noise figure, SDR sharp or SPI, is about 3.5 dB. And so here, using the results of these calculators, the results of no attenuator after the preamp, using one of these preamps, comes out to be, with a half a dB noise figure, it only degrades it by 0.2 of a dB. That's with 24 dB gain and a 3.5 dB noise figure following it. The overall system noise figure is 0.52 dB. If you have a 10 dB attenuator behind that amplifier, preamplifier, then the noise figure degrades to 0.69 dB. If you put a 15 dB attenuator, it degrades to 1.1 dB. 20 dB noise pad will degrade the overall noise figure to 2.1 dB. And if you use a 24 dB pad and you have a 24 dB gain, but you get rid of all of the gain, the noise figure is now worse than the receiver alone. In other words, you've lost 0.2 of a dB. So that's the unusual characteristics. You no longer have this half a dB noise figure preamp if you kill a lot of gain behind it, is what I'm saying. And so I know that some of the guys don't understand that. Go ahead.
Hey, Ray.
Yeah.
Just as an FYI, I have a 10 dB attenuator after the preamp. And
Okay.
the reason I put that in there was I was told that the SDR front end can overload if you put too much gain from the preamp into it. That's why I put it there, but maybe I don't need it.
Actually, no, that is true. You're more sensitive than to overload. The more gain you have, each stage can actually overload, and that's why I put the filter between the first and second stage up there. Is just to keep other signals, because these are very wideband preamplifiers that we use. I don't know about this particular one. This one is probably not. That has already some selectivity built into it, but that just shows you that you no longer have this half a dB noise figure that you thought you did. But on 6 meters, it doesn't make any difference whatsoever anyway, because the noise coming in on the antenna determines the signal to noise ratio. It's much higher than this 3.5 dB noise figure of the SDR. So that being the case, noise figure is not an issue. You can't use it. So going on a little bit, if that answer your question?
Yep.
Hope so. Okay.
I
Let's
have
go
a
on
small
down.
comment, Ray.
Yeah, go ahead.
Yeah, I just want to comment that, what Case about the SDR and 10 dB pad and the noise figure and all that. Well, the golden rule is more gain you have and more noise. So you can't just get rid of that physics. But if SDR pole is maximized gain, so if you have all the settings and put an auto gain, you're actually compromising your overall noise figure. So you have to switch to the manual, get rid of 10 dB pad, and maximize your gain out of the preamplifier, because the preamplifier noise figure is less than the SDR receiver. So you always maximize the receiver on the front end towards the antenna and reduce, as Ray's saying, the signal at the receiver. In your case, 10 dB is actually doing worse. So that's what my suggestion would be.
Yeah, okay. Yeah, the noise level on the speaker, on the output of the receiver, goes up, but the actual sensitivity, the front end noise figure, is what you're worried about. That's this guy up here. That follows the preamp. If you've got enough gain after it, and don't destroy it, just don't destroy the gain. But even 10 dB pad doesn't ruin it very much. Like I say, on 6 meters, it doesn't make a difference anyway, because there's so much noise on the band anyway when you get down to these kind of noise figures. Let me go on to the next one here. Okay, stuff to remember. The first stage has no filtering on the input, so any and all signals present might cause overdriving, resulting in intermodulation issues. And that's something that we faced down at Haswell. And particularly this last time, we were looking at a lot of aircraft flying over, and they when they transmitted, I'd never seen them before, but they were down there the other day, and when we were trying to do pulsars, and I don't think they were strong enough to do intermod, because any signal that overdrives the amplifier, then you get everything that's coming in the front end intermods. So be careful of that. The second stage can be overdriven if it's not filtered first by the interstage filter, and there you're getting rid of anything, in our case, below about 300 megahertz, and getting rid of everything above 400 megahertz. But if anything in that range can certainly cause overdriving of particularly the second stage and the SDR down in the building. Any transmitter at the site could overload the preamp, even with interstage filtering. So down there, we always have to, we have an AM station down there. That's why we have it turned off when we're actually trying to do pulsar work, because we could be susceptible to, say, even 6 meters getting through the filter up there. It's not that good a filter. Now, continue. In this case, a potential transmitter is any source putting out a milliwatt or less. In other words, you can have very small transmitters, even in computers, down there and have enough energy to get up there. And when we get the cascaded gain, if it happens to put out a signal within the passband 200 to 300 megahertz, or 300 to 400 megahertz in this case, excuse me, it could cause intermod issues up there. It could overdrive the actual later on stages. Any signal that causes a stage to overdrive causes all signals to mix, producing many spurs. And there are lots of signals coming in there. So once you overdrive one of the stages somewhere, you get a lot of mixing action and it gets pretty noisy. So that's basically, I think, what I wanted to talk about. I have, is there any questions up on this? If not, then I want to show you a couple of things that I've been doing here at my own ham station. And that's, I do radio astronomy work here, and I have a 12-foot dish. It's an all metal dish that we used at radio stations for a while. And this is looking at 1420 megahertz. This is a total power program. And you'll notice a bump right here, because this normally should go real smoothly right through here and back up. So these down here are from part of the galaxy that's moving away from us. And so I was looking at my antenna, not at the core of the galaxy, but out toward the edges of the galaxy through the Milky Way. And that's the hydrogen that I got. In fact, it actually is higher than the hydrogen I got from some of the other looking in toward the center of the galaxy. Surprisingly enough, I didn't expect that, but that's what it shows. So you see some hydrogen here, and if you put your cursor on this when it's live, this tells you what the amplitude is and what the frequency is, and it can even tell you down here what the speed of the hydrogen is moving either away from you in this area or moving toward you over in this area. So this is higher in frequency, this is lower in frequency. So that's a typical run that I did Saturday evening. And the next one I've got here, and this is one that you can have fun with. This is noise from the sun at 1420. And so this is about 14 dB from here up to here. That's a fairly good amount of sun noise. I think I could tweak that and get a little bit more, but that's not too bad right now. And a little side lobe on the antenna right here, but nothing on the front side. I was surprised because when I change feeds, I get other side lobes on it. But with this particular feed, which is a horn feed at 1420, I get just this little bump on the outside here. And so I was real happy with that. This is much better than the log periodic I used for a long time because I was looking at other frequencies as well. But the noise that I got from the sun using the log periodic was only about 5 or 6 dB at the most. And this one's 14 with the horn feed. So much better feed. And on to the future. And I think that's it, Myron. Thank you.
Ray, what was the SDR that you're using for these plots?
For this one right here,
Yeah.
this plot is a Nuelec little SDR, just a little dongle. It's the
Okay.
same as the RTL SDR dongles, but it's Nuelec's version of it. It's a little better than the normal ones that you get.
Yeah.
And it's just the smallest one. Yeah, but that's all it was. And
And
the
it-
total power program.
And do you have the preamps in front of it, or what's the configuration?
Yes, it does have a preamp right out at the antenna and about 30 feet of line coming in, maybe a little bit more. But there is a preamp right up there. It is a Nuelec preamp that they sell. It has about 40 dB worth of gain with a SAW filter in the middle of it. In other words, 2 stages with the SAW filter, very similar to what I build down for the site. And it has a noise figure of about a half a dB and a gain of like almost 40, right close to 40 dB.
Okay.
What your broadband band preamp? What's the frequency coverage on that?
Well, in this particular case, the coverage is much narrower because it's only for hydrogen.
Okay.
And the bandwidth is about 30 megahertz, I think, something like that on this frequency.
Are you using hardline for your coax?
No, you gave me the hard line, the cable, I think. It's LMR 400
600. Big
mostly.
stuff. Yeah, LMR 600, the big stuff. Anyway, thanks a lot, Ray. Any questions? Any more questions for Ray? Ray does all our antenna building, preamp, installing, for, all the listening devices up there when we switch frequencies. And what's the schedule now for the feeds? You gonna leave the feed up there, your current feed, until we change it out for EVE?
Well, I may change it again, and I may, because of some conversation with Dan when we did the last Pulsar run, I may go and switch that to the 420 feed, the one that we originally got the first Pulsars with,
Okay,
the dual dipole one.
okay.
Hey,
Yeah,
Ray,
that I may do that. Yeah,
Ray, you were talking about 365 megahertz.
correct.
Did you have any success hearing the pulsar that was originally found by what's her name? Can't think of her name.
Jocelyn Bell.
Jocelyn Bell.
No, we did not get that one. We did try, or we tried one of them. Dan can correct me on that. We did try one of them, another lower pulsar. In fact, I think we tried a couple, and we didn't get any other pulsars other than our same calibration pulsar that we always use. We call the 54 pulsar.
Right. Okay, just interested.
Yeah, the 377, we were listening down there during the open house, and there was an air traffic control ATC center. Denver Center has a remote station down there just north of Los Animas, and they were transmitting on 377, or was it 375.175, something like that. Anyway, they had a remote down there, remote transmitter, and it kicked out quite a good signal. Then we were also hearing a few megahertz away some military aircraft conducting the air-to-air maneuvers with several, might have been AWACS or tankers or fighters. You could hear that conversation going on as well. So there is activity up in that portion of the band.
Yeah, was that little station, was that north of La Junta or north of Los Animas?
Los Animas.
Okay,
Or I get those guys mixed up down there. Might have been Lahana.
okay. Yeah, I thought that's what you said originally. Oh,
Yeah, Lahana.
okay, very good. Thank you.
Yeah, you can find it on an IFR en route chart. All right, well, Glenn and Lewis, you guys are up next. So you got the screen. You can go for it and give us your presentation there.
Okay, does everybody see that okay?
Yep,
Yep.
it's good.
Okay, great. So this will be a really quick presentation, one chart. All I'm really going to talk about is what we're going to be doing down at the site tomorrow. We're going to travel down tomorrow morning, and we'll be performing these following 5 tasks. The main task for us down there is to take the new operator console PC, which Paul Sabone got for us, and we're going to install that and replace the laptop that's sitting down there. And once we do the replacement of the PC, then we're going to check out both the 12-bit and the 16-bit systems, the automatic and manual processing. I already have those installed on the box here, and I've checked it out with the simulators and thing. So I'm hoping that'll be a relatively easy thing to do once we get down there, but you never know what's going to happen. So that's the main thing we want to do once we get down there. In conjunction with that is that on the 16-bit software, there's some software fixes for ambiguous zone processing and for Venus tracking. So we're going to definitely check out the ambiguous zone to ensure that it's working correctly. The ambiguous zone is where you slew into a place between 15 degrees on either side of 0. And if you bring it down or bring it up, the software gets confused. And we've made a fix to allow the operator, if they do bring it down or bring it back up, to move out of that area. So we'll be verifying that fix tomorrow. And then the next thing is we're going to collect some mount characteristics data. And that data we're going to collect kind of flows into what our new design for our track processing. And Lewis has got a presentation after this my presentation that he'll go through about 10 charts about the modifications that we're looking at for track processing. Then there's this other thing that I've just recently started calling a combo system. And what that is the actual Raspberry Pi software and the operator console software, the client and server software, both of those will be running on the new PC that we're taking down there. And I've got that up and running here. I've made some minor software modifications. And what I want to do down there is I want to run the CPU utilization program to see how much CPU we're using by having both of those systems running simultaneously on a single box. I was running that today a little bit, and the CPU utilization tool indicates there's 4 CPUs, and we're making use of 2 of the 4 right now. So, but that looks pretty good. But we'll see what it looks like once I get down there. Now, we may or may not want to get rid of the 16-bit Raspberry Pi. There are definitely some uses for it where we could use it as a display device or something, but we can talk about that down the road. I just wanted to see if it was feasible to see if we could get rid of the Raspberry Pi if we were worried about RFI kind of things for Dan. So I'll be looking at that. And then the other thing we're going to look at if we have time is we purchased this this industrial non-managed PoE internet switch. It's got 4 ports on it. We can use it for the encoders. And their operation range is much better than the one that we have up there right now. It runs from like -40 Fahrenheit to 174 degrees Fahrenheit. So we're going to look at one to see if there's a power coming off the power supply that we have in that enclosure. And 2, and if that isn't there, we need to look to see how long we're going to need to run maybe an extension cord or something for that power. So that's the other thing we're going to do. And if we do have time and if everything goes well, we may go ahead and install that switch. So those are the things that we're looking at down at the site tomorrow. Any questions on that at all? Okay, I'll bring up Lewis's presentation. And okay, can everybody see that?
Yep.
It's called tracking modifications.
Yes.
Okay, are you ready, Lewis?
Yep, go to the agenda page and there's been some question. We've been looking at upgrading the tracking algorithm over the fall, and there've been some questions on it. So wanted to kind of get out in front of the group what we've been looking at, and see if there are any questions, concerns, whatever. I'm probably going to try to go fairly quickly here so we don't take up too much time, but please ask any questions whenever you have one. Kind of this first subject would be basically to take a quick look at the current tracking approach so we can contrast that with what the modifications we're talking about making. And once we've kind of described the modified approach, then we want to look at some kind of performance considerations, and that really comes down to looking at the tracking signal loss using the updated algorithm, and also looking at how frequently the mount is commanded. And what I've listed here is step, drift, interval, and as we get into, you'll see why that name is there. So that's been a concern that to try to minimize how often we're updating the mount position. And so we'll talk about how this algorithm affects that. And then what it really comes down to in the end is there's a trade-off between you won't reduce signal loss, you'll incur a reduced or increased commanding frequency. If you can tolerate a higher signal loss, then you can command the mount at a reduced frequency, and the slides will indicate why that is. So I think I want to get to this first slide on the current tracking approach. Just as brief history, this current capability has been out in the field. I don't remember exactly when it was fielded, but it was 3 to 4 years ago. And prior to the fielding of this, the mount was positioned and tracking was conducted using the front panel of the manual control capability, and it was pretty tedious to do. So we tried to field fairly quickly a capability that would have the computer control that, and we basically mimicked what the operators were doing when they were throwing the switches to position the mount where they were. And so with the idea that a kind of a more sophisticated approach would be taken after that, well, it's now 3 or 4 years later, and so we've started finally getting around to it. So on this page, this plot is a plot of tracking for one axis an object that's moving at a fixed rate. And so just for explanation, the x-axis here is time, and then the y-axis is the position of the object. So in this case, the object's moving, or target's moving at a fixed rate. And then you'll notice there's some dotted lines on either side of the tree, and those are really that's the threshold where we're trying to maintain the axis between those two upper and lower thresholds or bounds. So the way the tracking algorithm works right now is, let me see, I'll start here where the axis slew is initiated when pointing error threshold exceeded. Basically, the axis is at 0 rate at that prior to that, and the object is basically drifting, and since the axis is 0 rates, the object is gradually getting farther ahead of the axis. At the time that the error threshold between where the axis is pointing and the object hits the threshold, then we turn on the mount, and it's turned on at a fixed rate. And then when the mount gets inside of the threshold, we turn it back off. What, a subtlety that happens here is our update loop is running at once per second. And we, and for the axis step rate is 0.1 degree for the azimuth and 0.05 for elevation. So basically what happens is that step it'll step for 1 second and then turn the mount off. You'll notice that the axis position basically never even gets to the object position, much less goes over on the other side of it. And then when once it's inside, we set the rates back to 0, and then again go back into a drift type mode. And it'll drift until it hits threshold again. That cycle just repeats over and over. And so you can see from the diagram with this approach, there's a pointing bias. The axis is always below or in effect behind the object. Now, if the object was going negative rates with this, with the trajectory pointing down, it'd be the opposite. It'd always be somewhat above it. The other effect of this is that the axis commanding frequency is higher than necessary for accuracy. If when we powered the axis on, it went farther and closer towards the target trajectory, or even beyond, then the drift phase would last longer, and that would reduce the commanding frequency. So, and commanding frequency has been a concern with respect to wear and tear on the mount. So that's the current approach. The software receives position data from the Pi at 10 times a second, but the tracking update loop currently only runs once per second. And there's some reasons for that. You'd probably be able to run the modified loop at a higher rate when we move the software down onto the new machine. Right now, we let me see, excuse me. We have the tracking threshold set to 0.1 degree for both axes. And that's the way it's been pretty much from the beginning. We use a higher step rate for the azimuth than the elevation. I think early on we were using 0.1 for the elevation, but it seemed to cause some instability. So we dropped it. It caused the instability and overshooting and such. So we decreased that to 0.05. I believe that was done before the 16-bit encoders were added, but
Yeah, it was.
so when we went to the 16-bit encoders, we did not change any of these tracking parameters. They're the same as they were. And basically, so the track basically works as it did with the 12-bit. The big difference in terms of, and it's not really a large difference, is it can more accurately discern when it crosses, the tracking threshold is really what happens with the 16-bit encoders. So we'll go on to the next slide here. And so we're going to contrast the old approach with this new modified approach, and kind of label it the step drift tracking, because basically it consists of a cycle of stepping and then drifting. So, which the current algorithm does, but the difference is the algorithm is modified to when it steps to go over all the way to the opposite boundary, opposite threshold. And so that maximizes the amount of time that you can get drifting. So just as what we see, the box with X is driftlet interval, it shows that when the axis rates are 0, the target catches up and passes the axis position. And then the duration for that is the object is actually moving 2 thresholds worth of difference, and it's moving at the target rate. So the duration of that drift is 2 times the threshold divided by the target rate. So from that, we can see the duration of that interval is directly related to both the threshold and the target rate. And I'll show some slides later on that, show that relationship. Then at the point where the drift crosses the threshold, then we turn the mount on at the step rate and step up to the boundary. In this case, we're thinking right now that we'll step both axes at 0.05. The primary reason for 0.05 really is that's the slowest rate that the elevation axis can move at without being turned off. So the step interval duration is similar, the formula is similar, except that it's basically the threshold distance is being crossed at the rate of the slew rate minus the target rate, since the axis is catching up with the target. It has to, you have to subtract off that rate. the net result is the slew rate or step rate is much higher than the target rate, so the step phase is much shorter in duration in general, and so the overall duration for the step and the drift phase is mostly driven by the drift phase. So in this example, I was just, you can see the statistics or the parameters for this particular track. The target rate is 0.004 and degrees per second, so that's pretty slow. We'll talk about what the expected rates are here in a few slides, but that's beyond what you'll ever see on the elevation axis, but that's a fairly nominal value for the azimuth axis. The slew rate of 0.05 and then threshold of 0.1. While it's not relevant on this slide, we'll start it later, but it's using a half power bandwidth of 0.81, which is really the bandwidth for a 1420 megahertz signal. In this track, what we see is a max signal loss for this one axis would be 0.183. The duration of the step time is 4.3 seconds, and then the duration of the drift is 50 seconds. So the overall cycle time is about 54 seconds for this one. And one of the things is that with 0.05 slew rate, that's roughly 10 times as fast as, you know, our actual tracking rates that mostly we need to achieve. So that means that in general, we're going to have duty cycle of about 10% on and 90% off for the mount, depending on the mount rate. Let me see.
So Louis, you're saying that the parameters, the outside parameters of the what do you call it? The threshold.
Right.
How far is that from the center line or the track of the object?
The 0.1 is the distance from the object line to the dotted line.
That's
You know,
0.1 degrees.
0.1 degrees, and that's in a vertical direction is the way. Like for instance, on the 50 time mark, you take that vertical mark, the distance from the blue line down to the blue dotted line is 0.1, and then the distance from the blue line up to the yellow dotted line is 0.1. And basically that's the position, and that position moves along with the object. Yeah. Is that make sense or?
Yeah, it does. Well, that's what I'm wondering is because our 3 dB focal zone of the dish is
Right.
around 0.8 degrees at 1420.
Right. I think
And-
the next slide might
Yeah.
So this is just an example.
show the kind of, I think what you're getting at. And
Yeah, go ahead. I'll shut up.
yeah, I think, you know, that previous slide was only for one axis, and you have two axes. So this slide shows the pointing error for both axes, and just to kind of describe that, you see the 3 dB line or circle, and that's
That's the outside circle, right? Yeah.
that's the outside one. I also plotted some, you know, lower dB circles just for reference. And so the green line is actually the threshold. So the upper and lower horizontal green lines are the thresholds for the elevation, and then the left and right green lines are the thresholds for the azimuth. And with this algorithm, what it's supposed to do is to keep the amount within that square, basically. And you show, and this is with 0.1 here at 1420. So it shows that well, we talked about what the loss was, and we'll see in the next slide even better description of what the loss are, but it's around 0.17 or so on this spot. So
0.17 dB.
right.
Why are we trying to do this so accurately?
Bill, this is an example. It is not what we're trying to do.
Okay,
This is just an example.
well, okay, all right.
what we're trying to set this up is so you can vary that threshold.
Yeah.
And so, in fact, I'll show some slides, some plots later on at different thresholds and what it means with respect to signal loss and with respect to how frequently we're commanding the amount. And that's the trade, your trade accuracy versus how frequently. And, you know, you might make a different trade depending on whatever the mission you're trying to run. So, but I chose 0.1 in this case because that's really the threshold that we've been running with. And I think it's, I would call it a happy compromise between the two. But, you know, that there may be other choices. So,
Well, let me just make a point here. The reason I pushed this so hard for the last year and a half or 2 years is we're driving the mount very rapidly. We're driving the mount very often, and we're literally putting a lot of wear on it that we don't need to put on it. And if we're within a 1 dB threshold, I would think that we'd be fine, or even a 2 dB threshold. There's very few applications of this where I can see that we want to be down at this accuracy level. And the trade-off is that we're driving the mount so often that we're wearing out all the mechanisms.
yeah, what I would, one of the point I would like to make is if we run this algorithm at the same threshold as the current one, it'll roughly drive them out about half as frequently just from going to this new algorithm.
Yeah, half's not good enough.
And
not from my
then,
viewpoint.
Well, I'm not trying to set a threshold. We're trying to come up with a system that'll allow the threshold to be set.
Yeah.
And there are we'll see the plots that show the trade-off, and it's not necessarily a directly linear relationship. So, but you'll see them later on, and it'll give you information about, you know, threshold versus update rate.
Okay.
I agree that I think this method is undesirable from the standpoint that we're turning them out on and off. If we could run it at slower rates, then I think that would be less wear and tear. That's just not available option, particularly with elevation axis. And we're proposing to use this for both elevation and azimuth,
Yeah.
just for consistency. But, so that was the points I was wanting to make about this slide. Go on. So we're going to look at the signal loss in a little more detail, just so everybody will understand what's happening. This is the same example as the previous foresight view, is just presented in the, you know, a different plot method. And so basically in the example, the as target rate was 5,000th of a degree per second, and the elevation was 2,000 degree per second. And those are fairly nominal rates for as and now. Then you can, when you look at the commanding interval, it's about, because the as is running faster, it's running, in this case, at 44.4 seconds. And the elevation is quite a bit slower, and so its update intervals around 104 seconds. So what this means is down below, the lower chart shows the pointing error in the blue. And then in the red or orange, it shows the loss. And these are 2D values, not just due to one axis. So, you know, the error in each axis combines to create a larger error than either one of those axes. And basically it combines using, you take the overall offsite foresight error using Pythagorean equation, and then you apply that off foresight error through this tracking signal loss equation, which is a pretty standard equation. And that gives you the 2D signal loss. And so just explain the patterns here. It's not just a random noise. It's really, you know, occurs as a very periodic way. Basically what happens is when you're going through the drift phase, you drift from a maximum error. You drift through where the object's very near the bore site, which gives you minimum error, and then you back out to the next, the other boundary. And so that gives you this scalloping shape. And there's, since we have two axes, it running that where the target rates are different, we basically have two scallop shapes overlapped and combining in the kind of the short scallop shapes occur when the mount is stepping from one boundary to the other, and that gives you those short ones. So basically what happens, it kind of goes from maximum loss to minimum loss back to maximum loss in a period of, you know, the steps take around 3 or 4 or 5 seconds. So you see, you know, a quick change, and then you see a much slower change when you're drifting. So, you know, if quick changes cause issues, then this method can potentially cause some issues. It's not just a steady, gentle change.
Right,
And
but
this,
it's still only 0.5 dB as in that lower plot, right? Is that the lower plot is the combined?
the lower plot is the 2 dB, and the max value, it's over on the in the blue box, is the maximum, which occurs around 100 and whatever that is. Can't read that.
If I look at the axes, it looks like 0.3 dB or so is the one over here on the far right hand side is about what, 0.4 dB?
That one is, well, the number is 3.373.
Oh,
In the
okay.
blue box, Bill.
So
Yeah, I see it.
that just, you know, because the as and L can be because of the target rates can be different, this diagram, you know, it'll differ, but the basic scallops, short and long scallops, will be in all of them.
So hypothetically, if I said we could tolerate 1 dB, I'm not saying for everything we could tolerate that, but certainly for EMI and most things we do, we could probably tolerate 1 dB. We could reduce the mount exercise to a third of this, right?
Not sure I'm not sure it scales that way. We could revisit that on later charts.
Well, that's what I'm saying. We were asking for a way to select that, and I guess you'll get to that, but
Well, actually, the way you select it's on this chart, it says signal loss equals 12 times port side error divided by the high power bandwidth squared. If you rearrange that equation so that you state offsite error as a function of signal loss, then you say, okay, I can tolerate whatever signal loss, you plug it into that equation, and then it tells you what the offsite fourth site error you would need to reach that.
right.
And I haven't shown that, but that's how you would do it. It's a pretty straightforward equation.
Bill, I think on the previous page, their dB loss, it showed probably you could go for 0.2 or 0.25 for a 1 dB loss. You know, it was the one with a little box in the center. If you could you roll back to the previous page of the there. So yeah, 0.25. So, you know, technically you could go for like a 0.25 approximately error for a 1 dB loss in this case.
Right.
There is one other flying Neumann, and that has to do with how the rates of the object in a particular part of the sky.
Right. It varies wherever you are, for
Right.
sure.
Yeah.
Yeah,
Yeah.
Well, I have a slide to illustrate that. And so what you will not be able to do is say, I want the mount to update every 200 seconds, period. You have to accept that, you know, it'll be based on object rates.
Right.
You
I'm
can-
not saying that. What I'm saying is if we could select the bore site size.
Right, and that's, you know, we have not gotten down to implementing those types of features and whatever, but we anticipate doing that. And we would try to do it in what I would expect is, like you say, the operator would specify the amount of loss that he can tolerate in his mission, and the software would select the threshold that would achieve that. But then at that point, you have to accept whatever those
That's fine.
update interval is for that selection.
Yeah. Yeah, and it's going to be, you know, if you select a much larger bore site size, that
Right.
interval is going to increase. And that's what I'm aiming for is I'm just
Right.
afraid we're going to wear the mount out by the time we figure this out.
I don't think that's gonna happen. Lynn has this,
Well, we've already broke a chain.
well, I don't know why that chain broke, and I don't think. we
And-
do either.
And so there's wear. I mean, every time you drive the mount, there's wear. And just listening to it, we know there's wear. And so what I'm trying to do is say, okay, we've got one thing to play with here. And originally it didn't do this. This happened after we added the algorithm. We actually did have an interim algorithm that took a lot longer between cycles.
This is the algorithm that was built in.
That's the one we've always had.
No,
Yeah,
it changed.
So I wrote
I'll,
it.
I'll let it go. Okay. Just that's my input. Okay. We gotta open this up.
Right.
Yeah,
agree.
Go ahead, Glenn.
Yeah, I wrote all the software that has to do with a lot of the stuff, and I know when we changed it, when we didn't change it. So this is what we basically had. Now there was once upon a time when we were doing stuff with the front panel of the manual mount control. Then you could actually do what you're saying, but
Yeah, it wasn't manually done. It was done on the system, but there was an interim system before this particular code level. Or what we have now, not this code level, but what we had now.
Yeah, and Bill, that chain is how many years old? I don't think you can
No,
ascribe.
that's not my point. All I know is that we're driving the scope much more often than we need to drive it to get the accuracy that we need. That's all I'm saying.
What one concern I had is it sounded, Louis, it sounded like you said something about describing how many dB we could tolerate. I think it would be more useful for us to describe, how many degrees or tenths of degree off we want to be, because then we can experiment, because that will give us the dB drop off. So I think it'd be more useful for us to be able to describe the arc of error, or arc of I forgot what you called it, threshold, rather than a dB drop off, since that's going to vary for frequency and everything like that. Just
That's right.
allow us to specify an angular.
That's right. That's going to vary for each different feed and frequency that we use.
Yeah.
So, yeah, Roger's right.
Yeah, I mean, we're open to anything as far as how the operator communicates to the software. I mean, we can all take a look at it. It's not that big a deal. We just need to pick a solution eventually.
Yep. Okay, I'll shut up now. Go ahead.
You're fine. That's why we're talking.
I think that's the points I wanted to make on that.
Okay.
Why? Since we made the point that the target rates are one of the, if not the key driver, well, there's two key drivers, the threshold and target rate. So I wanted to show what kind of target rates we might encounter. And so primarily our primary targets in radio astronomy are beyond the solar system, which means the targets are sidereal rates in general. And so these tables show what azimuth rates would be at a specified elevation in azimuth. So like, for instance, at 180 azimuth and let me see, say 0 elevation, the azimuth rate would be 0.0026. And one of the things you'll notice, and particularly on the 180 degree azimuth, as you get higher, the rates get higher. And in fact, when you get close to 90, they get, at 88, I think the max is 0.09, which is pretty high. And so that's the way to read this chart. That upper table shows you, it's really, I've structured it as a heat map. And what I tried to color code it to show, really slow rates are in blue. And by slow, it's 0 to 0.002. Kind of semi-slow, I guess you'd call it, is 0.002 to 0.004, and that's in the green area. And then yellow, it's rates between 0.04 and 0.01. And so those are getting faster, and the update cycles will start to grow. And then, the highest rates are above 0.01. And so you can see where in the sky those will occur. And basically for azimuth, just the higher you get in elevation, the rates get higher. So let me see on elevation, the elevation rates, the table works exactly the same, except that it do the elevation rate for a given azimuth combination. And there's a real definite pattern here. It's basically in the east and the west, the rates are the highest. And then along the meridian, 180 and 0, the rates are the lowest. And that really is because it rises in the east, and so it's going up, and then as it crosses a meridian, it's 0 and then starts going back down. So that really explains why. So the range of value for the elevation is the fastest rate in this table is 0.00327. Given the granularity of the table, the max elevation rate might be a little bit higher than that, but will be quite close to that. And the min L rate's 0, whereas on the azimuth, the min as rate is well, it's essentially 0. It's 2/10,000. And the max as rate up to 88 degrees is 0.09. And I've shown it below 85 degrees. It's my opinion, we shouldn't be tracking things up above 80 or 85. So it's getting a little too fast. And let me see. So that's sidereal rates. The other things that we track for moon bounce, we track the moon rate. And the moon actually orbits the Earth in the same direction as Earth rotation. So what that really means is its L rates will be slightly, it'll be below the sidereal rates for any given position. One of the things, I think the highest the moon can get here is around 80 degrees. So around 180 as the rates can get fairly high for when you're tracking the moon. Planetary rates are most likely fairly close to sidereal, but that it's going to vary because of the relative position of the Earth and whatever planet you're interested in. So I didn't try to characterize what they're really going to be. So right now, I think the only planet we're talking about tracking is Venus. And some analysis has already been done about rates, around the time that the EVE will be attempted. So that's the rates that we would expect to encounter. This chart is just a plot of the step drift interval as a function of the target rate. And now there's other factor in it is the threshold. So I plotted this at a set of thresholds from a pretty tight threshold to what I consider a fairly loose threshold. So the upper one is the threshold at 0.2. And then the next one down is 0.15 threshold, 0.1, and then 0.05. And the way you can read this chart is that you can take a target rate you're interested in, and just to do one that's easy, 0.005, and you go vertically up until you hit a threshold plot line, and then go across to the y-axis and read off what the interval would be. So if you have a really tight, let's say at 0.005 for a really tight 0.05 threshold, you're going to be, the update interval is going to be around 20-25 seconds. If you run, if you go all the way up to a 0.2 threshold, then the update interval is going to be around 90 seconds or so. So that's the way you read this chart. What you see is that at the faster rate, the thresholds don't make as much difference as they do at really slow rates. And we're, in terms of elevation, we're probably going to be sitting, most of the time, the rates are going to be around 0.002 to roughly. And so that vertical line is the kind of update intervals that you would encounter there. So it'd be anywhere from 50 to 200 depending on your threshold. Let me see, azimuth, it varies more, but I think it probably, it might cluster more around 0.05 or so. And so you'll see that you can't get as long an intervals at that rate. But so just as the thick way increasing track threshold increases the step drift interval, increasing target rate decreases the step drift interval. So that's about all I was going to say about this chart. We can go on to the next one. So this chart is kind of the final wrap up. This is where we're showing the trade between signal loss, which is a function of threshold, which then in turn determines a step drift interval. So in this plot, you can start from a given signal loss you're interested in, go horizontally across until you hit the target rate of interest, and then drop straight down, and you can read off what the update interval would be. For instance, a 1 dB signal loss, come across till you hit the 0.004 degrees per second and drop down. That's 110 roughly. So, I didn't show some of the higher rates like 0.01 and above, and those just get less frequent. So, but what it does show is you can really get quite infrequent when you're running really slow target rates. But at the higher rates, you don't have as much flexibility.
But correct me if I'm wrong, but this would be, for example, a specific frequency and or feed, because that signal loss is going to change depending on what frequency you're looking at. Is that correct?
I don't. Let me think about that. This doesn't assume a specific, well,
because the beam,
that's
beam
true.
wider.
Because, if you're running at 400 megahertz, you got a huge leeway compared to 1420.
Were all these done at 1420, Liz?
I think this was at 1420. I have to go back and check that. I was kind of basically just doing worst case.
Yeah. And the target rate, we don't really, from the previous slides, the target rate is what the object's moving at, right? So that's going to be whatever it's going to be.
That's correct.
Yeah. Okay.
Right. You have no choice but that. And so and the point I want to make about that is, if you're watching the lights on that panel and see it blink on and off, and you see it blinking more frequently, that doesn't mean the algorithm changed or the parameters changed. That means you're in a different part of the sky where the objects are moving faster.
Right. Different target rate. I get it.
Right. So you can't really just look at that. You got to take into account where it is. And,
yeah.
But the point I was trying to make here is that, because I think you said that you believe this was done for 1420.
Right.
When you do get around to giving us a knob, I think that the angle is more useful than trying to base it on dB, because again, that's going to vary depending on what frequency we're looking at.
Yep.
Well, I guess it depends on how critical signal loss is to you. But in any case, we could allow the operator to specify a threshold. In the software, we do allow them to specify frequency, and it could compute the signal loss for that threshold also. And, he could set, oh, I want to set it to a point, whatever, and then he could see how much he's going to be penalized or not in signal loss.
This is gonna get more important as we look for more OH groups. And those are small. That frequency is gonna be much higher.
Right. I, originally took 1420 as I thought the worst case, and then I realized that Dan was doing some maser work in 1600 and something, so yeah. I will say is I don't think tracking pulsars with dim ones, you can tolerate 1 dB loss. Especially with these the way it moves around.
Yeah, and we're getting into weaker and weaker pulsars, so
Right.
it's gonna get critical.
So I agree for moon balance. As long as you got a lot of margin on your signals, then
Yeah.
Well, for some things, we have a lot of margin.
right.
And,
Yeah.
if we go to 10 gigahertz, the beam width gets smaller and then it matters more. But at 1420, 1600, it probably, we're probably in overkill. Dan might disagree with me. I don't know. But I think we're in overkill right now.
Well, and we can also, if the knob was an angle, we can experiment and actually characterize what we're seeing.
That's right. Yeah, I don't want the program to tell me what the signal loss is. I want to look that up. I want to specify the beam width. I want to specify the beam width and then go from there, or specify the update angle,
Threshold.
the threshold, and go
Basically
from
the
there.
threshold, how far you want to wander off.
Yeah.
Remembering the rate plays into all this stuff, object rates.
Yeah, but that isn't going to matter if I specify the threshold.
No, it won't.
I mean, sure, at a higher rate, it's going to update more often, but that's fine. I'm accepting that the rate's going to, we're going to update more often with a higher rate. That's totally acceptable because you can't do anything about that.
Exactly.
Right. Ideally, we'd like to have a whole different gear train and be able to drive continuously, but we don't have that. We've got a bang bang control system. And my point is to try to minimize the bang.
Yeah, we're not gonna track any low Earth orbit satellites with this thing.
That's yeah.
Well, what I would say in terms of wear and tear, actually I was going to talk about slewing to the target, but I kind of forgot it. But when we slew, we command amount on azimuth axis to 0.4 degrees per second, which is about half of the commanding range. And we command elevation to 0.2 degrees per second. Before we get to the target, 3/4 degree from the target, then we command down to the step rate. So that when it ramps down, it's there's not a big jolt at the end when you're stopping in the tracking range. One comment, well, it turns out that both of the command or the motor controllers are basically rate controllers, and they handle the ramping up and the ramping down of the rate. So if we command it to 0.4 and we're sitting at 0 rates, it will accelerate the mount up until it gets to the commanded rate, and then smooth out the acceleration.
Yes, sometimes it's
Those
better
are
to-
all set. Pardon?
Sometimes it's better to keep it moving than to start, stop.
Yeah, we just don't have that option because the minimum rate for the elevation is 0.05 degrees per second. And I believe that is due to the type of motor controller and motor we have. It's a VFD, and those can't run at zero rates or very near zero in general without the motor controller can actually specify that, but I don't believe the motor is not designed to do that. So basically the motor controller for the elevation axis won't let you go below 0.05. And to go to zero, you have to turn it off. And when you turn it off, then the brakes fire. And that's really undesirable behavior, but it's what we got. And
Hey, one comment I could have here. It's Paul, Alex, when he was changing the chain for the azimuth, he noted that the speed at which that thing turns, just to get a 1 degree change, he had to pull that chain down many times in order to get it to move even 1 degree. So if you ran that motor slightly slower, you would get much less starting and stopping. Right now it's turning at pretty high RPM to turn the dish. If you could slow it down a bit, you could run it continuously, I think.
I think we could run the azimuth close to continuous, but we have, right from our early testing, it looked like the slowest it would run at was around, I don't know, 0.01 or 0.02 degrees per second, which is still above the sidereal rates. I haven't gone back and re-verified that, but at the time, everybody thought it was probably stiction. I don't know if that's really what it was or not, but
Could be.
Is
Okay.
there such a thing? Is there such a thing as a variable speed motor for those?
Well, the whole gear train would have to be, I mean, with enough gearing, you can run, down to
Right.
zero. But that's the gearing that's in there. We're stuck with what we've got, and we don't have really a way to change that out. We're basically working with the original gear train, but with different motors. The original motors were counter-rotating 5 horsepower motors with a magnetic eddy current clutch in between them. And so the way they drove the dish was to move that clutch with an amplifier, and the eddy currents would pick up one motor magnetically or the other one. And so they were able to drive very slow rates by keeping the motors running at the same speed. That all got taken out because we had no way to drive that system. All the amplifiers were gone. And when the original founders came into the site, they put the motors that the servo motors that they had in Boulder, and the power controls, the VFD controls that they got from these are the same VFD controls that run things like industrial lines. The guy that did all that work was a employee of the Budweiser plant and did can lines. So you can imagine, 1 million cans running down the line at light speed. That's what he used. So those motors is what we have, unless somebody wants to pony up a proposal for whole new gear train, which would be a massive undertaking. This is what we've got.
Is the azimuth motor a fixed speed motor, or can it be varied?
It can be varied.
So, I mean, one of the super simple ways to, if you wanted to drive the azimuth slower, is because those chain teeth are worn. You're looking at replacing those at some point in time. You can change the gearing ratio.
Yeah, you could change the gearing ratio of the chain.
Yep.
If there's room. But, there you could maybe pick up, 2 to 1 or something, but you still have this problem where you've got, we think it's 65 tons sitting there on those bearings, and we're not even sure what the bearings are. And there is stiction, you got to get, and there's a lot of MO. There's a lot of angular momentum. You've got to move to get this thing off at ground zero, right? And so you can only go so slow.
Actually, I'll try to add it to my list. If I've got some leftover time tomorrow, I'll try to go up and count the number of teeth on both of those things, since we're gonna probably have to replace one of those
Yeah,
sooner or later.
I think Alex did that, and I think we have that data.
Alex,
Yeah.
Paul, do you have that
We have
data?
a photo, we have numbers, Roger.
You got numbers. Okay, never mind. Saves me some work.
You can still go.
I could what?
You can still go there.
Yeah, if you're curious. But I think we're running, you're probably running it about right for speed, Glenn. I don't see, slowing it down has issues, because right now, I mean, it stalls. You can hear it stall in the azimuth direction. And so, I don't think you can run it much slower. You're muted, Glenn.
This is kind of the point why we're going down to the side is we're trying to collect map characteristic data. So look at the logging of the data as the map begins to move, as it goes to where it needs to go, that type of stuff. So we can see if for one, if it's consistent and repetitive, and then using that to help us understand how to drive it.
Yeah.
So that's our plan.
Okay.
And to go back just completely, I think we're going to provide some type of operator interface to allow them to manipulate what they need to get their job done. Basically, if we're chasing the moon, it doesn't make much sense to have a threshold that's real tight. If we're chasing a pulsar, maybe that's something else. But I'm not the person. We're not the people to do that. Someone has to decide what makes the most sense.
Right. Dan says 1 dB sounds pretty good for pulsars.
Okay.
So that's just, doesn't have to be 0.1 dB.
Well, we'll provide the capability if we ever get it done. We're old and volunteers.
Oh, yeah. Right. Aren't we all?
How close we are to wrap this up there, Lewis?
We got one more chart, I think.
Yeah, we got, this is just the kind of a high level plan we're working to. We've prototyped this new modified algorithm. I prototyped it in simulated it in Excel, and then Glenn has implemented it in the operational software, although all the mods are not complete. There's enough there, I think, that we can do some testing at the site. He's tested that in Colorado Springs with a simulator, and then tomorrow we want to make some runs with that at the site. Yeah, hopefully we can get all enough information in one trip to be able to verify the approach. Then got to do clean up some additional issues in the code so it'll integrate in with the operational code, and then go back through the test process in Colorado Springs and at the site. So hopefully we can get through this in the next quarter or so, but depends on weather and every other thing. So that's all I had. If there are any more questions,
That sounds really good, guys. Thanks for accommodating all my stupid questions.
Glenn and Lewis, you guys have done a super job on this stuff. It's just been such an improvement all the way through. I remember twisting the knobs to track. So
it was like Pac-Man.
Oh yeah, it was a fun game, but it got tiresome after a while,
Yeah.
So
yeah, I call it Zen meditation.
much like that, yeah.
Thanks, Lewis. Thanks, Glenn.
Thank you.
Hopefully you have a great trip tomorrow. Weather should be good.
Should be.
And again,